is 1, which means that cosine of theta is 1. Well, indeed, cosine of 0 is 1, so theta is 0, and tan of 0 is 0. Okay? So actually, the only thing you have to be careful of is, are we sure it's 0 and not, for example, pi? 2 pi, rather? Well, it couldn't be pi, because cosine of pi is minus 1, but it could be 2 pi, right? So perhaps, is it 2 pi? Well, no. We've got to make sure we're in... You know that you've got to know the ranges of inverse cosine, inverse secant. And the answer is it's 0 to pi. How are we doing? We're doing well. We have it. Okay, I'm going to finish this example and then we'll start filming. Okay, as for this one, here you probably have to be a little more careful. And I don't know what cosecant inverse of minus 2 is, or do we? Suppose that cosecant of minus 2 is theta. This means that cosecant of theta is minus 2, which means that sine of theta is minus a half. And you just have to find the right theta that makes that work. Okay? Can anyone tell me a value of theta whose sine is negative a half? Someone? Sorry? I want a theta that solves that equation. Pi over 6? Minus pi over 6. Okay. Can anyone tell me another one? 5 pi over 6 is in the second quadrant, and actually the sine of that is 1/2. But 7 pi over 6 would work. And another one might be 11 pi over 6. Which one is the correct value of theta that we need for this? You need to know what the range of inverse sine is, and the range of inverse cosine. Does anyone know what it is? The inverse sine of something is between what and what? Negative pi over 2 and pi over 2. What it means is, although there's infinitely many solutions, this is the one we have to select because it's between minus pi over 2 and pi over 2. So this is minus pi over 6, and then you just have to find sine of minus pi over 6. And sure enough, sine of pi over, this is minus 1/2. And it's not surprising, actually. You're welcome. Okay, so here's the plan. I'm going to erase this in a few seconds, so I start with a clean slate. And then I am starting the official lecture, and maybe it'll just run short. Did everyone get this yet? Well, maybe I'll erase all this. We had some technical difficulties with the sound. And I already have to redo one of the second lecture sometime because the sound wasn't working. Actually, there was no microphone, so that's probably why it wasn't working. But I don't want to have to redo more than one. So well done getting that ready. Thank you. Okay. Check, check, sound, lights, camera. Okay, hello, welcome back. We're going to continue this evening with a little bit about the differential. We did linearization last time at the end, and I mentioned about the differential, but I'd just like to look at one example involving the differential that I didn't have time to do last time. There is also a section in the book about, at the end of the linearization section, in chapter 13, about the error in linearization. And because that is not in the Math 103 syllabus for this semester, I am going to skip it. However, we will cover it eventually in Math 104. That's the second half of the book when we do Taylor series and the remainder term. That will subsume what I would have said anyway. So again, I skip that. I'm going to deal with the differential. But then the rest of the time, this time, I'm going to do Chapter 11 of my book, which is about graphing, but not so much sketching graphs. It's the impact of the derivative and the second derivative on graphs and functions in general. So we have to look at that. And it's sort of setting us up for next time, which is going to be just all sketching curves, sketching graphs using calculus. So that's the plan of attack. Anyone have any questions before I delve into this plan? Well, all right. Let's start off with a brief review of the differential as it was from last week. We started off with a function f depending on some variable x. And actually in my example, both of these are going to have other letters, so I don't want you to think it has to be f or it has to be x. And the idea was that we have some special point A. We have some special value. It's like a springboard, the launching point for this. And there's a value A, and we know all about f of A. For example, if f is the square root function and a is 9, great, we know the square root of 9. We don't know the square root of 11 or 10 or something like that very, very well, not like we know the square root of 9. So this is what I mean when I think of a as a special value. It's a nice value. We know all about f of a. And the idea was we were going to change a little bit. We were going to change a into x. And, of course, if you do that, f of a changes to f of x. And the idea is we'd like to know what f of x is. So we're going to use f of a as the springboard to f of x. So we're going to change a to x. F of a changes to f of x. We can't get at f of x directly, so we're going to use f of a to help us. And we're going to use it by using the tangent line. So if this was the graph of y equals f of x, and here is our special point A, this is our f of a, which we know all about, and here's our other point x, we would love to know this height here. That's the perfect answer that we want. Unfortunately, we do not know it, so we're going to use the tangent line through here. That's the linearization, L of x. And this quantity from the actual value to the nice value is delta f. That's the actual change in f. So we've gone and changed a up to x, and we're going to change f of a up to f of x, and the amount I'm going to write as delta f. But this is the approximate amount, df, and that's how I defined it last time. df, so delta f is f of x minus f of a, so that's the actual change. When you change from a to x, whereas df, well, we found out last time by using some calculus that df is f prime of a times x minus a. That was part of the linearization. I want to put this in perspective by thinking of this quantity as delta x. So it's the amount I actually changed x from a up to x. I changed it by delta x. Then actually x minus a is exactly the quantity delta x. And if you look at it, all this equation says is that df, the differential, over delta x is equal to the slope of the line. So it's the rise over the run, and of course the slope of the line is f prime of a. So if you rearranged this equation to read df over delta x is f prime of a, you would get something that just says rise over run is the slope. Anyway, without much ado, all I want to do is just say that we're going to say that the actual change we want is approximately equal to this, and there is our equation for a differential. The actual change is approximately equal to the approximate change from the tangent line, which is the derivative at the nice point times the amount you've changed it by. That's what that says. Now, let me see if I can bring it a little bit to life by looking at a fairly, well, a nice example. It's not that difficult, but nevertheless, it's something that seems a little confusing when you first see it. So here is an example. Suppose I have a ball, like a soccer ball or something. I have a round ball, and I have some ruler that's, or a tape measure that has pretty wide markings. It's not a very accurate sort of thing, not very precise. So basically, I measure its diameter just by holding up this ruler against it, and I measure it as 6 inches, but I'm not very sure. I'm going to assign plus or minus 0.5% as an error to this. So it could be a little more than 6 inches, could be a little bit less than 6 inches. But I actually don't care about its diameter, I care about its volume. I'd like to know, what is its volume? With error in both absolute terms and as a percentage. That's the question. What is the volume of such a ball? And how accurate do we think we are? This is a problem that uses the differential. Now, I should say with error, I'm going to say approximate error. I'm not asking you to find the true error. I just want you to approximate, get a good idea for what the error would be. Okay, so let's see how it works. First of all, we're going to need a formula. I'm going to, perhaps against my better judgment, let the diameter be capital D. You should never use little d as a variable because you go dx or something like that. That just doesn't work. But capital D, I think, will be okay. So let the diameter be V and the volume be V. Now, it's supposedly a sphere, so we know that the formula for a volume of a sphere is V is 4/3 pi r cubed, where r is the radius. Of course, the radius is half the diameter, and we kind of want to deal with the diameter. So I'm going to convert this to d over 2 all cubed. And if you cube this out, you get d cubed over 8. 4 over 8 is 1/2. And you will find that you have v is pi over 6 d cubed. Okay, so if d is equal to 6, that's the diameter which we've measured, volume is pi over 6 times 6 cubed, and we get a bit of cancellation, and it turns out to be 36 pi. Now, so the volume is 36 pi cubic inches cubed, but that would be, there's no calculus, I've just used the formula. Well, I've left a space here because I'm going to put a plus or minus, and that's really what the question is asking. What is the error in this? If it was exactly 6 inches diameter, sure, the volume would be exactly 36 pi, assuming it was an exact sphere as a ball. But it's not, so we have to do a bit of work. So we're going to need the derivative. So from there, I'm going to find dv dd, which for sanity's sake, I'm going to just write v prime of d. See, think of this as, if you like, v of d. Maybe those aren't such great initials to use. Anyway, v of d is pi over 6 times 3d squared, which is pi over 2d squared. So, when d equals 6, well, how do I even know that? Let's write down the equation here. We're interested in the error in v, or the change in v, is approximately dv, which is equal to f, well, it's not f prime, it's v prime of d, delta d. Okay, that is just the above equation, but all I did was I replaced f by v and the variable x by d. Now the thing is, this d is the original d, which actually we know is 6. So I'm just going to change this to 6. Now, in order to see what's going on here, I would like to just draw a little graph. This is D, and this is V. And when D is 6, V is 36 pi. And I am proposing that we change D by a little bit, which is delta D, and see what that does to the volume. If I change this by a little bit, what will that do to the volume? See, because I'm only accurate to 0.5%, it might be a little higher or it might be a little lower. The true value is somewhere in some little range. So that is what this delta D is. It's the uncertainty. It's how much I could possibly vary D by from 6 and still be within my measurement error. And of course, that will induce the change in V. So what is delta D? Well, it's 0.5% of 6 inches. So I better take a little sidebar over here and say that 0.5% of 6 inches is actually equal to 0.005 times 6, which is equal to 0.003 inches. So in absolute terms, I've measured, is that correct? 0.003, it's not 0.003, it's 0.03. I was out by a 0. Right, so I've measured it to 6 plus or minus 0.03 on either side. So the true value is somewhere between 5.97 and 6.03. But in any case, in this formula here, I can take V prime of 6 from this as pi over 2 times 6 squared. And I can take delta D as plus or minus, if you like, 0.003. And I will get as an answer, it turns out this is 36 over 2, so it's plus or minus 0.54 pi. That's the actual answer. And I computed this on a calculator, don't tell anyone, as about 1.7 cubic inches. So if I come over here, what I have shown is that the error is about 0.54 inches cubed. No, 0.54 pi, please. Got to have a pi there. Okay, so that's the absolute error. Just to recap what we did, we found the actual volume. That gives us this. But for the error, all I had to do was magnify the original error by the derivative. So I took the derivative of the formula, plugged in the 6, which is the nice value, as according to the A specification. That told me the magnifying factor here, and then the error just got magnified by this much. Okay? So this is sort of interesting. The one thing I wanted to comment on is that to get that number, I had to convert the original percentage into the actual absolute answer. I still have not finished the problem because I'm supposed to work out what the percentage error is of this. Well, of course, if you know that the volume is 36 pi, the percentage error is equal to the actual error over the quantity itself times 100%, which is equal to 0.54 pi, approximately equal to, because actually this is an approximation itself, over 36 pi. And if you work that out, you get 1.5%. That's what the number works out to be. 1.5%. Okay, so what I've shown basically is that we knew the diameter accurate to 0.5%, but the volume we only know to 1.5%. It's 3 times the error, relatively speaking. Relatively speaking. We are 3 times as uncertain about the volume relative to the actual volume as we are about the diameter relative to the actual diameter. Okay, and the number 3 is not an accident. It's not an accident at all. 3 dimensions. Anyway, so any questions about that example? No questions? Well, in that case, I dispense with the whole differential linearization thing, and I'd like to move on, or back, as it were, to chapter 11, and talk about how the derivative and the second derivative affect graphs. So, new topic, backtracking even. Okay, so the first thing I'd like to do is remind you of the concept of a global maximum or a global minimum of a function. So, by example, suppose I have a function. This is going to be height 3. I'm just going to mark in some points here. Okay, so I want the function to look something like this. Okay, so the function's domain is 0 to 7 inclusive. Question is, and this is not supposed to go through the axis until... Okay, good. It has a y-intercept at 3. No asymptotes, nothing fancy going on here. Just poor drawing on my part here. Okay, so the question that I have for you is, what is the maximum that that function attains on that interval? Well, the highest point it gets to is 3. That's the maximum value. We actually care about what the x-coordinate is. So we have a maximum value of 3 at x equals 0. So somewhat confusingly, we say 0 is the maximum, not 3. 3 is the maximum value of the function, but 0 is a maximum. Now, I'm going to use the word global maximum. Some people also say absolute maximum. I prefer global. Global means the whole world, right? So as far as the whole world is concerned, that is the maximum. Absolute, global, everywhere. That's the highest value it gets is 3, and it occurs at 0. Of course, if the function had gone all the way up to 3 again, the maximum value would still be 3, but there would not just be one maximum at 0, there would be 2 maxima. One at 0 and one at 5. 2 global maxima. So there might be more than one. On the other hand, the minimum value of -1 occurs at x equals 2. And these are global max and global min. So there's nothing new in what I've just said, because we already knew what maxima and minima were. In fact, we even had a theorem called the max-min theorem, which had nothing to do with differentiation. It only had to do with continuity. Just to remind you what it said, if f is continuous on some closed interval, f has a, well, I'm going to say a global. I didn't use the word global before, but that's what I meant. A global max and a global min. Somewhere. So that was a theorem that we learned. There's no, if it's continuous, it's sort of tied down to the ends of the closed interval, and what's more, it has to be drawn in one piece. So there's only so high it can go, or so low it can go before giving up. It can't have asymptotes. It can't do something funky like just keep getting higher. It has to stop somehow, and that is the content of the max-min theorem. And as I said, we did that way back in chapter 5, and you don't even need any derivatives to do it. The problem with this theorem is it does not tell you where they are. It does not tell you how to find the global max and min. And that is where we're going to start using the derivative. Okay, so before I use the derivative, I need to introduce what's the opposite of global? Local, as far as math is concerned, right? Global is the whole world. Local is just really right here. Very close. So I like to try to define the concept of a local maximum. Okay, and to me, the best way of doing it is, imagine that you are actually walking, this is a mountain, and you're walking up and down the mountain. It's a two-dimensional snapshot, obviously, but you're just walking up and down this mountain. Now, when you are at 3, there's a cliff here, so you want to avoid it, but when you're at 3, you are at the highest point. That is the peak. But what are you going to say about when you're at 5? You're not at the highest point, but it sure feels like you've climbed up and then back down. It feels like you're at a maximum. So we ought to call this something. We're going to call it a local maximum. And the best way I can describe it is that as you are near it, imagine that a big fog descends and covers up everything except for this little part around you. You've only got 20 feet visibility, which makes it difficult to climb, I guess. I've never really climbed a mountain, so I don't know. But basically, if the rest of it was all in fog, this would be the global maximum. It's just you're no longer global, you're only restricted to a very small locality. So a local maximum, so we're going to say x is a local maximum if f of x is a maximum, or a global maximum, when you restrict its domain enough. So, for example, you don't have to restrict the domain very much to find it's a maximum. You just don't want to pick up any of this stuff over here. But you cannot say that this is a global maximum or even a local maximum, because no matter how you restrict your domain, you'll always pick up a point higher than it. So that's a sort of technical definition. In reality, you probably just need to have a good intuitive idea of what makes a local maximum. And that is basically it's higher than all the points around it, near it. It's the local peak, near where you are. And the same thing for local minimum. So, I said that I was going to help you find these maxima and minima. We just have to make sure we understand whether we're finding global or local maxima and minima, and there is some relationship between them, of course. So, here is what I would like to say. I've got to use the derivative somehow, so let us say that x equals c is a critical point. As in, it's pretty critically important to it. For f, if f prime of c equals 0, or if f prime of c doesn't exist. Remember, sometimes derivatives don't exist. Function can have corners, and I'm going to consider those to be critical points. Sometimes, I don't know, this is the only definition, but I'm going to say that both possibilities could occur, and I'm going to call it a critical point. Okay, so what is the point of using critical points? We've got this extreme value theorem. And of all the things that are called extreme in your lives, this is the least extreme. Because extreme here does not really mean way out, whoa, dude, that sort of thing. What it just means is a maximum or a minimum is called an extremum or an extreme value because it's either the highest or the lowest. So as far as f is concerned, they are extreme. So that's why it's extreme here. So basically it says that if C is a maximum or a minimum, and now I should say a local max or a local min of a function f on an open interval a comma b, say, then C is a critical point for f or of f. I don't remember. For, of, who cares? Okay, so basically, maxima and minima occur at critical points. But it does not mean that critical points must be maxima and minima. It's the other way around. You can have a critical point that is not a maximum or a minimum. And we'll see some examples, but here's a very sort of straightforward example. If you have a curve like this, where you have a point of inflection, it's a horizontal tangent line that goes through the curve like this, the derivative is 0, so this is a critical point here. Right? F prime of c is 0. And yet, this is neither a maximum nor a minimum. It is a point of inflection. Okay, so do not think that critical point means maximum or minimum. Instead, think maximum or minimum means critical point. Now, by the way, consider the absolute value function like this. Okay, what is the minimum of that function? Someone in here can tell me what is the minimum of that absolute value function. How low does it go? 0. So the minimum value is 0, and it occurs at x equals 0. Okay, is 0 a critical point? What's the derivative here? Does not exist. So it is a critical point. See, that's why I'm putting in this does not exist as a possibility. It's one thing to have this. Now the derivative here is 0, and it is a minimum. But maybe the derivative doesn't exist. So let's just try to look at why this is true. Suppose you do have a maximum, and that the function is differentiable. So here's a maximum. What could the slope be there? That's a local maximum. What could the slope be? It has to be 0. To the left, the thing's lower. To the right, the thing's lower. It has to be 0. That's not a proof. There is a proof in the appendix of the book. That ain't the proof. Okay? Nevertheless, there is an idea that if the derivative were positive, then we would be increasing there, and so you have to be a little bit more to the right. In fact, we'll even look at a proof when we do the mean value theorem a little later in this session. Maybe in an hour or so, towards the end. Okay? So the same thing, of course, goes for a minimum. Okay, so that is the extreme value theorem, and although it wouldn't be a bad idea if you learnt how to state it, actually, the main interest in it is that we're going to apply it. And what I'd like to do is show you, as soon as I've finished erasing all this stuff, I would like to show you a method for finding global maxima and minima using this theory. Any questions? If you have one, just holler it out. All right, no questions? So, I'm going to try to come up with a method, or show you a method, of how to find global maximum and minima. So, actually, before I do, maybe we can go back, and focus on this picture right here. This is a local minimum. It's also a global minimum. The derivative there is 0. That's a critical point. X equals 2 is a critical point. X equals 5 is also a critical point, but this is only a local maximum. It's not a global maximum. So what about 0 and 7? Those are endpoints. They are endpoints. The derivative actually doesn't exist there either, so they're sort of critical points. You have a left-hand derivative, a right-hand derivative there and a left-hand derivative here. But I don't know whether to call them critical points or not. I'm just going to call them endpoints. And as you see, this endpoint is a global maximum. It's also a local maximum because every global maximum is also a local maximum. Every global minimum is also a local minimum. Okay, this is a local minimum, but it is not a global minimum. because you're lower down here. Okay, so a refinement of that theorem that I just put in is that if f is actually continuous on a closed interval and differentiable in the interior, then maxima and minima, local if you like, or global, these theorems are both true for local and global, must occur either at critical points, and in this case f prime of c equals 0. The derivative cannot not exist. It must exist because I'm assuming it's differentiable. Or the endpoints A and B. Those are the only possibilities, right? So you can either have something going in the middle, but then the derivative has to be 0, or you might just have the endpoints. And that previous example that we looked at, that picture that we just focused on, is an example of where one of the endpoints happened to be a global maximum. So this suggests the following procedure to find a global maximum and minimum, or all the global max, and minima of a function, of such a function on a closed interval like AB. Okay? So the first thing is find f prime of x and find where f prime of x equals 0. So we want all the values where it equals 0. Now there might only be one, there might be none, or there might be many. So make a list. So you write down all the places where the derivative is 0 in the interior. Right? Sometimes a function will actually be, you could define it on a greater interval, but we might say, oh, just the domain is, 2, 5. Well, you don't need to worry about anything outside 2, 5 in that case. So you just find the points where the derivative is 0 in AB. 2 is to add the endpoints to your list. And the endpoints are A and B. Okay, so our list consists of all the points where the derivative is 0, as well as the two endpoints. 3, plug every value, each value in the list, into the equation y equals f of x, and not the derivative equation. We're actually going to plug them into the original equation to find out what are the heights of the function at these different points. 4 is pick the maximum, pick the largest, I should say, of these values. All the x coordinates that produce it, or corresponding to this, are global maxima. Remember, there might be more than one that produce the same height. And similarly, smallest of the values, and this will give you the global min. Okay, so I'm going to illustrate this with the following example. Suppose that f of x is equal to 12x to the 5th plus 15x to the 4th minus 40x cubed plus 1. And I'm just, even though this could easily be defined everywhere, I'm going to define this on the domain minus 1 up to 2. And I want to know where are the global and maxima and minima. Where are the global maxima and minima of this? With respect to its domain, minus 1, 2. Well, following this prescription, we differentiate. We get 60x to the 4th plus 60x cubed minus 120x squared. And we can factor this as 60x squared outside of x squared plus x minus 2. And we can actually factor this further into x plus 2, x minus 1. So that's the complete factorization of this. And this is clearly equal to 0 when x equals minus 2, 1, or 0. But this one does not matter. I'm going to ignore minus 2 because it occurs outside the domain of this function f. If, of course, I let f go free and be the whole, have domain all of R, yes, it would matter. But you've got to ignore it in this. So our list currently looks like this. List of potentials is 0 and 1. Well, according to this, I need to add the endpoints of the interval. The interval is minus 1, 2, so I need to add those to the list. So I've got 4 potential candidates for the maxima, the global maximum, and the global minimum. So, how do I know which one is which? Well, I just plug them in. Plug it into y is f of, say, minus 1. That's one of the ones on the list. If you plug minus 1 into the original equation, you get minus 12 plus 15 is 3, plus a further 40. So it's 43 plus 1 is 44. You don't even need the y equals. You can just plug in 0 and you clearly get 1. That's easy to see. You plug in 1, that's another one on the list, and you get 12 plus 15 is 27, plus 1 is 28, but then minus 40, I get minus 12. And finally, f of 2, if you plug that in, it's a bit of a mess. I mean, 2 to the 5th is 32. So I worked it out on paper once upon a time as 305. It's not a very difficult computation, but you still have to do it. So which one is the maximum and which one is the minimum? Or which ones are the maxima and which ones are the minimum? Well, the answer is that the highest value is at 2, so that must be the global maximum, and the lowest value is at minus 12. So the conclusion is that x equals 2 is the global max, and x equals 1 is the global min. And the minimum value is minus 12. Bless you. So you see, we didn't really have to know much about the function. We had to know more about its derivative, and in particular where the derivative is 0, in order to find out what was going on. Now that actually solves the problem, but we might as well draw a picture of the situation, see if we can understand it even better. So the domain is minus 1 to 2. At minus 1, the height is at 44. So this graph obviously has different scales on the axes, if that's minus 1 and that's 44. X equals 0, you get a height of 1. X equals 1, we're all the way down to minus 12. And x equals 2, we've catapulted up to 305. God, that's all the way up here. Something like that. So the graph actually must look something like this. It's probably not vertical there, but that's what the graph must look like. How do I know it looks like that? Well, obviously I know what those anchor points are. How did I know that this was like this? Well, I know its derivative is 0. The derivative is 0 there, so it must be flat. And we found that it's a global minimum. Well, that's consistent. I've drawn this consistent with this. On the other hand, how do I know this is an inflection point here? Well, again, the derivative is 0. So it must be that. Wait a second. Why couldn't it do this? So why couldn't it go all the way down and back up and then around? That would still have derivative 0 there. Well, the reason is because this can't happen. If this happened, we would have found it, because the derivative would have been 0 somewhere in between here and here. I don't know where. Maybe right near here or closer. But there's no way it could dip down below and come back up without producing another critical point. And we know it doesn't because we found all the critical points. So this must be what it looks like. Not with this dipping down. It must be like this. And the only potential candidates for global maxima and minima are this, 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 and this. And we can clearly see that 1 is the lowest and 2 is the highest. All right, so just beware. Just because you don't have just because you do have a critical point does not mean that you have a local maximum. Actually, this picture has allowed us to see that this is not even a local maximum or minimum here. We could have even told this directly from this thing. Now, it's just a coincidence that it happens to be all the integers here, of course. These are the endpoints, and these are where the derivatives are 0. So, of course, it could have been half or minus 3/4 or something, but it just worked out nicely in terms of the numbers. All right, so that is how to find global maxima and minima on a closed interval. Before I move on to something a little bit different, what if your interval that you want to maximize on is actually unbounded? What if it is an infinite region? I'll draw you a picture of an example. Of course, you can come up with actual functions that are examples, but suppose I have a function f whose graph looks something like this. So it starts at 0, it goes up here, and then it has a horizontal asymptote here. All right. What's the maximum value? What's the maximum value of this function on its domain from 0 inclusive to infinity? And where does it occur? Global maximum, please. Someone tell me. Okay, the maximum is at 2, and the maximum value is 3. How about the minimum? The minimum is at 0, and the value is 0. Now, if you tried to use the previous method, you would find there was one critical point here, crit point at x equals 2. There's an endpoint. What about this endpoint? There is no right-hand endpoint. But maybe the right-hand endpoint doesn't matter. Actually, it sort of does matter. Instead of the right-hand endpoint, you might sort of want to consider using the limit as x goes to infinity of f of x, which in this case is 1. So I sort of think of the right-hand endpoint as infinity, and instead of plugging in f of so my list is really 0, 2, and infinity. F of 0 is 0, f of 2 is 3, and f of infinity doesn't really make sense, but it does make sense as the limit as x goes to infinity of f of x, which is 1. So the highest point is 3, and the lowest point is 0. But there is something subtly wrong with what I've been saying, although it does work in this case. If I just change the picture a little bit, suppose I change the picture so that it still has this maximum up here, it still has this horizontal asymptote, but it starts at a height of 2. Okay, if we try to repeat this, we again have 0, 2, and infinity as our endpoints. This time f of 0 is 2, f of 2 is 3, and f of infinity, again, is 1, if you interpret it as a limit. So what's the biggest of these values? Well, this is the largest value at 3, so x equals 2 is still a global minimum. No, global maximum, rather. Question is, what is the global minimum? Well, according to this, x equals infinity is the global minimum. And the minimum value is 1. I put question marks after there, because how can infinity be a global minimum? What does that even mean? Infinity is not even a number. So that can't make sense. Is the minimum value 1? Well, for that to make sense, the function would actually have to be 1 somewhere. So that function, as I've drawn it, with the asymptote getting closer and closer from above, it never gets to 1. So actually, the minimum value is not 1. This thing does not have a minimum value. It does not have a minimum value, and that does not violate the max-min theorem because it's not a closed interval. This is what can go wrong if you allow open intervals. Okay, so the point here is that the minimum does not exist. And mathematicians have a fancy word because it looks like there should be something like a minimum, and they call it infimum, and there's also supremum for the maximum, but that's beyond this course. That's a part of an analysis course. Real analysis starts looking at infimum and supremum and all those sorts of ideas. But, you know, it's good to know that you should consider at least the limit so you have think of that as an endpoint. So you have some idea of what's going on. It just could be kind of complicated. And we're really at the fringes of what is testable in this course, at least at Princeton and probably in most other places, without delving into some real analysis. Okay, so that's what I want to say about maxima and minima for the time being. I need to do a few important theorems. But first, are there any questions?
How do you get given a closed interval that you get given like from -1 up to including 1? You know what I mean?
Okay, so the question is, what if you have an interval that's open at one end?
Well, if it's up to and including, does that mean the same thing?
Closed interval means up to and including. So when I say closed, I mean, you know, like for example, this interval over here, -1, 2, is a closed interval, and it includes -1 and 2. Things are tricky when you do not include the endpoints, though. And it's a similar sort of scenario. I'm going to draw a quick graph of a similar sort of thing. If I just draw, say, for example, the open interval -1 to 2, and I just have a function as simple as this. On that open interval, you see it's not defined as at the endpoints. This doesn't have a minimum or a maximum either. You'd like to say the minimum is -1, but that cannot be true because that's not in the domain. You'd like to say that the minimum value is 1, but it is also not true because 1 is never actually achieved by the function. Okay, the function never is at height 1, so it's wrong to say, oh yes, the minimum value is 1, because it gets close to 1, but it never actually gets there. So that's when you start using words like infimum and blah, blah, blah. So again, that's gotten out of the touch. So basically, this stuff works well on closed intervals because you have the endpoints that ties everything down, and they are the possibilities. Here there's no endpoints, and yet the endpoints should be the answer. They can't be the answer because they're not in the domain. So you sort of like, what do I do? Take a course in real analysis, I guess. Or otherwise. It's your choice. Anyway, let's get through calculus first. Okay, so then I need to tell you about two theorems, which are actually the same theorem in two different ways. They just look different. The first is called Rolle's theorem, THM for theorem. Here's what it says. suppose I have a function, and let's suppose that it's continuous on AB, and that f of A and f of B are equal. So that means that the function begins and ends, if you think of this as starting here and moving to there, it begins and ends at the same height. And what's more, I'm going to assume it's continuous, as I say, and also that it is differentiable. No spiky corners or anything like that. Well, suppose it starts going up. Guess what? It's got to get back down. Where does it have to go back down? It could leave it quite late, or it could go back down quite early. It actually could go down as well. It could come back up. There's all sorts of things it could do. But what goes up must come down somewhere. And even if it only does it once, there must be a critical point. There must be a point where the derivative is 0. Of course, it doesn't actually have to go up. Maybe it starts off by going down. Well, of course, if it goes down, it has to go back up somewhere, and there will be a point where the derivative is 0. The only other possibility is maybe it never goes up or down and just stays at the same height. Well, if it stays at the same height, it's constant, and its derivative is 0 everywhere. So basically, that's not a proof, again, but it's a good sort of heuristic rationale, if you like, for why this should be true. If f is continuous on a closed interval AB, and it's important that it be closed, meaning, of course, it includes A and B. Like this. It's continuous from the right here and from the left here and everywhere in between. And it's important that it is differentiable on the interval A, comma B. It doesn't really matter what happens at the endpoints for this particular thing. Then there is some number C, at least one, number C, in the interval AB, open, where the derivative is 0. There might be only one, like here, for example, there's only one, whereas here, looks like there's quite a few. 1, 2, 3, 4, 5. But I know there's at least one. And that's the content of Rolle's theorem. Now, before I show you an application of this, let's look at a couple of cases where it might actually go wrong. Okay? There's no point here where the derivative is 0. It's plus 1 here, and it's minus 1 there, and it doesn't exist there. So what went wrong? Why does Rolle's theorem fail? Can someone tell me? It's not differentiable everywhere in AB. It just misses at whatever this point is here. So actually, for it to work, f has to be differentiable everywhere. Even one point can screw the whole thing up. Okay? My next trick is this function. This is supposed to be A and B here. Here is another function. This time, I'm going to make sure it's differentiable and continuous. Okay? There is a function. I think you'll agree, though, its derivative is not 0 anywhere. So what goes wrong this time? Why doesn't Rolle's theorem apply? Yeah, you need a condition that I have forgotten. So you see, I could pretend I did this on purpose. Yes, I meant to leave it out so I could show you why you need it. Actually, I screwed up. But anyway, if you could go back and make sure you insert this very important condition into your theorem, or the statement of the theorem, and you can see very simply from this picture why you need that condition. If it is not true, it can just go straight up from f of A up to f of B, or straight down if it was the other way around. So you absolutely need that. What about this? Let me rectify the situation. Same curve. I'll just take an open point there and define f of a to be at the same height. And yet, still, there is no point where the derivative is 0. What's gone wrong this time? F of a equals f of b. What's wrong? Exactly. F is differentiable even everywhere on the open interval, but it's not continuous here at a. So even just failing to be continuous at one point, at the end point in this case, is enough to screw up and you cannot use the theorem. Okay, so these are three cases where the theorem doesn't apply because your function does not satisfy the three conditions. It has to be continuous on the closed interval, differentiable on the open interval, and the endpoints have to agree. All right. So, I have to tell you that this theorem has its main benefit, believe it or not, in proving the next theorem, which is the mean value theorem, and that is actually quite a nice, useful theorem, especially from a theoretical point of view, as we will soon see. But we don't even know what that theorem is, mean value theorem as it's called. So before I move on to that, I'd like to give an example of how we can use Rolle's theorem to prove something that I even stated last week. And I kind of copped out and said, well, you know what, I'm telling you it's true, I can't prove it yet. Well, I need Rolle's theorem to prove it. So here's what it is. Last time we looked at inverses of functions, right? We tried to use the derivative to see if a function had an inverse. And what I said was, if f prime of x is greater than 0, rather, so if f is always, if f's derivative is always positive on some interval on f's domain, say AB, then f has an inverse. I'll just say f has an inverse. And another way of thinking of this is, i.e., f satisfies the horizontal line test. Okay, I said this last time, but now I would like to use Rolle's theorem to justify this. Okay, so first of all, I've got to show you what it actually means to satisfy the horizontal line test. What this means is you do not have a horizontal line that intersects it twice. If you did, there would be no inverse. Of course, if it intersects it more than twice, you're even worse off. Actually, you're not really worse off. You still don't have an inverse. So you're not really worse off at all. You're still in bad shape. You're in bad shape. So you only need one time, or you need it to be only one time, rather. Okay. So how do we prove this? How do we prove that this is true? I'm going to use Rolle's theorem, and I'm going to argue by contradiction. Suppose, so here's the justification of that statement. Suppose f does not have an inverse, or does not satisfy the horizontal line test. Okay, so suppose that f screws up, and the picture looks something like this. I don't know what it looks like. Suppose there's a horizontal line which intersects the curve at least twice. Well, if it intersects the curve at least twice, then it does intersect the curve twice. Maybe more, but twice. And I'm going to pick two of these intersection points. So let's say then a horizontal line intersects the curve y equals f of x at least twice. Say when x equals a and x equals b. So on this picture, I have shown a horizontal line. It intersects the curve twice, and the x-intercepts are a and b. Okay. First of all, is f, and you know what, I shouldn't call, I've got myself in a tangle here. May I go back and change the original domain of the function to capital A, capital B, so that I don't get all confused. Here's capital A, and here's capital B. Whatever. Okay, so all I'm doing is I'm finding some line that intersects it twice, and I'm finding the x-coordinates. Okay, let me ask you this. What do you think of f? Is it differentiable? Is it continuous? What do we know about f? Well, it's differentiable on a to b, maybe not including these endpoints. How do I know that? Well, actually, not only do I know it's differentiable, I know that f prime of x is greater than 0. The very fact that I can say that means that f is differentiable. So the function is differentiable all over here, so it must be differentiable here, in between a and b, and it actually must be continuous all the way around from a up to b, so it is continuous even at the endpoints a and b. So we know that f is continuous on a, b, because it's differentiable on an even bigger region, and differentiable functions are continuous. And we also know it's differentiable on AB, again, and inherited it from its differentiability everywhere on the big interval. We also know that f of A equals f of B. Why does f of A equal f of B? Yeah, there's the same horizontal line that's going through this. So this height in this picture here is f of A, and it's f of B. Right? There's f of A. There's f of B. So of course, it's a horizontal line. F of A equals f of B. Therefore, we can use Rolle's theorem. By Rolle's theorem, f prime of c equals 0 for some c in the interval AB. Okay, so if there's the horizontal line, bang, somewhere in between, the curve is flat. So why is that a problem? So what? Can anyone see why that's a problem? Yeah. Well, I said the derivative is greater than 0. Yeah. But f prime of x is supposed to be greater than 0 for all x, including c. So that's the problem. It cannot be positive and 0. Notice I didn't actually need to know where c was. The very existence of it was an affront to my sensibilities, or at least the function f's sensibilities. Okay? That's a proof using a theorem, which we have not proved. So it's probably not truly a proof of this, and yet the theorem somehow is more intuitive even than the original statement here. So there is actually a proof of Rolle's theorem in the book. It's not that difficult. You just need the intermediate value theorem, more or less. Not that we proved that either. So I'm afraid we're in a tangle of logic here. But nevertheless, if the question were, prove the horizontal line test works if f prime of x is always greater than 0, using Rolle's theorem, this would be what you'd have to do. And I have seen such a problem asked on a Math 103 exam. Okay, any other questions about Rolle's theorem before I move on to the mean value theorem? All right, well, let's just partition this off, and I'm going to tell you what the mean value theorem is. I will state it first this time, and then I'll draw some pictures to describe it. So I want you, as we go, to think back to the Rolle's theorem. If you're in the room, it's easy because it's on the right board. If not, well, you can just look back at what you've just written down. But I want you to see how similar it is. If f is continuous on the open interval AB and differentiable, I'm sorry, it's on the closed interval AB, just like the other case, and differentiable on the open interval AB, then there's at least one number C in the interval AB with f prime of C is f of B minus f of A over B minus A. Okay. Just take a look at this for a second. It's very similar to Rolle's theorem. There are only two differences. The first difference is that we do not assume, and maybe we can pan over here, that condition which I forgot and have now underlined. That is not part of the mean value theorem. We did use it for Rolle's theorem, but we do not use it for the mean value theorem. It's gone. So moving back over here, the only other difference is instead of f prime of C equals 0, we now have f prime of C equals this mess, f of B minus f of A over B minus A. Okay. Before you, I don't know, panic too much about the formula, maybe you're not panicked about it at all, but, you know, let me just say that this theorem is basically Rolle's theorem on steroids. Because if you happen to know this theorem, and f of A equals f of B, then this quantity is 0. If f of A equals f of B, the top cancels out, and you do get 0. So this theorem, mean value theorem, includes Rolle's theorem. It is a super-duper, souped-up Rolle's theorem. So why even state Rolle's theorem by itself? Well, I don't know. I mean, it's a historical thing. You actually use Rolle's theorem to prove this. So the Rolle's theorem is the stepping stone on the way to this. So first of all, why do you even have this? What does it mean? And also, what do you do with it? What do you do with it? Well, let me spend a little time on what it means, and then we'll see some applications of it. But first, any questions? Again, you know the drill. You can holler it out while I'm erasing the board. I will listen. All right, no questions. So, let us try to work out what is the deal with this quantity f of B minus f of A over B minus A. So here's the picture. Suppose this is A, f of A, B, f of B. So what do I know? I know the function goes through here, it goes through here, and it's continuous and smooth and differentiable. So it's differentiable, no sharp corners, continuous, no jumps. Starts here, ends here, one motion. Okay, first of all, what is this slope here? Let's just draw in that line. What is the slope? Well, it's the rise over the run. The rise is f of B minus f of A. And the run is B minus A. Well, guess what? That is exactly the right-hand side of the expression in the mean value theorem over here. We can pan over. Look, it's the same. Okay. So back to the picture. Right. So what does the theorem say? It says no matter how you connect those dots, as long as you join them by a line that's continuous, or a curve rather that's continuous and smooth, there's at least one point where the slope is equal to this slope. And of course, if two lines have the same slope, then they are parallel. So what it's saying is there's a parallel tangent somewhere. There's at least one parallel tangent. Tangent is parallel to the secant. The secant being this line. It's just joining the, or if you prefer, line joining the endpoints. So there's at least one place. Actually, in this picture, there are two. But if the curve had instead gone up and down like that, there would only be one. But there can't be zero. It has to be at least somewhere. Even if the curve does this, there's going to be some point down here whose tangent is parallel. All these lines are parallel to the secant. Of course, the extreme case, as it were, is if the thing is just a line all the way up from there to there, and of course then every tangent everywhere is parallel to that line. The slope is always f of b minus f of a over b minus a. Okay, so that's called the mean value theorem. Why mean? I mean, it's a sort of mean expression, but that's not, of course, what we mean when we say mean. How many times can I use the word mean in a sentence? Look, it's like this. Mean also means average, as you might know from statistics. So when I say mean value theorem, it could have been called the average value theorem. But why? But why? I am trying to avoid using a Borat accent for that phrase, given that it's playing now, whatever. Anyway, never mind. The question is, why is it an average at all? Okay, well, think of it this way. Suppose that you consider this as a graph of time versus position. So think of this as time A and time B. And f of A is where you are at time A. And f of b is where you are at time b. Then this quantity, f of b minus f of a, is the total displacement. Like the distance, but it's the displacement that you've gone. And this b minus a is the time that it's taken. And if you prefer to think in distance, then you're just not allowed to backtrack. Your function cannot actually look like this. It might look like this, for example, or it could look like this, as long as it's always increasing. But you see, or it could have little wobbles like this. Okay? So the idea is that this is your total distance over your total time. Guess what? That's your average speed. And so, when I write down f prime of c, in this context, if with these interpretations of a and b being times, and b and a being, and f of b and f of a being positions, this is the velocity, or the instantaneous velocity, speed if you prefer, as long as you don't backtrack. And this is the average velocity. So what it says, the whole theorem, interpreted this way, says that there is at least one instant where your instantaneous velocity, as in the reading on your speedometer, is equal to your average velocity. Okay? In other words, if you are traversing a toll road and you take a ticket at the beginning, I know now you have Easy Pass, but whatever, you can do it computerized if you like. Look, if you have a ticket that says that you began traveling at 2 p.m. and then you go 120 miles, and that's where the end of the toll road is, and you get there at 4 p.m. and you give them the ticket. Can they book you for speeding? That's the question. The speed limit's 55. You've gone 120 miles in 2 hours. Can they book you for speeding? Well, I don't know about legally, but the fact is that your average speed was 60 miles an hour. Right? You've gone 120 miles in 2 hours. So your average speed is 60 miles an hour. But you say, wait a second, I wasn't going at 60 the whole time. How do you even know I was going at 60 at any of the time? Well, the mean value theorem. That's how you know. Unless you could somehow ensure that your motion was not differentiable, which might happen if you, I don't know, hit the shoulder or something. Then it might look like the absolute value. Bang. Of course, then you would worry about the absolute value of your car having gone down, and never mind that. Sorry, that was pretty bad. Okay, anyway, the point is that the mean value theorem says, look, if you average 60, you must have been going 60 at least for one instant. Now, the truth is, you might have been going 50 for the first hour and 70 for the second hour, right? But to get from 50 to 70, you would have had to pass through 60, even just for one instant. Okay? So the fact is, yes, your instantaneous velocity over any smooth journey must be equal to the average velocity over the whole journey for at least one instant of time. Hence the average, hence the mean value theorem. Okay? So that is a nice theorem. It is obviously true. It's obviously true. And yet, the proof is not obvious at all. So just take it as given that something so nice and obvious should be true, which is beautiful. Of course, it's not true if the thing is not differentiable or if it's not continuous. All sorts of things can screw up. If you're allowed to teleport, for example, then yes, you could teleport yourself halfway along the road and then just drive at a leisurely pace and not break the speed limit. But teleportation is not allowed because it is discontinuous in position. So, that is the story of the mean value theorem. Now, I'd like to give one example of it, and then I would like to give 3 consequences of it. So actually, I'd like to just clarify something. We started a little bit late. I know you can't tell if you're watching the video. We had a few technical difficulties. So is it okay if we finish a little late? Okay. So I don't know what our running time actually is because I didn't notice what time it was when we started. But I probably only have another half an hour of things to say anyway, which will put us under 2 hours for that part. And then, of course, we'll stop the cameras and we will go over the homework if anyone wants to do that. Okay, so without further ado, let me give you an example. And it's actually more or less the same example that we just did, but stated in a different way. Suppose that f prime of x is greater than 4 for all x. Okay, I've got some function whose derivative is at least 4. In fact, what the hey, I'll make it greater than or equal to 4. Okay. Show that the graphs of y equals f of x and y equals 3x minus 2, is it minus or is it plus? It doesn't really matter, but yes. So that the graphs intersect at most once. And this is an example straight out of 11.3. I should have mentioned the whole mean value theorem is section 11.3 in the calculus lifesaver. All right. So it certainly seems similar to the previous problem. I'd like to just give you the physical interpretation of it first. This 3x minus 2. Think of a car. If x is actually time, so 3t minus 2, and y is your position, then if you think about it, at time 0, this car starts at position minus 2. And the fact that the slope is 3 means that the motion of this car, I'm thinking of it as a car, is constant 3 miles an hour, or 3 miles a minute, whatever it is, to the right. So it starts at minus 2, and it's going 3 miles every time period. Say 3 miles an hour. Let's call it a lawnmower instead of a car. Okay, a jogger, whatever it is. 3 miles an hour. It's a pretty slow jog, actually. A walker someone is walking along to the right at a constant speed of 3 miles an hour, like this. Never changing speed. Okay, you are in a faster mood, you are a jogger, and you are always jogging at least at 4. You may be jogging, in fact, faster than 4 at different times, but you never slow down below 4 miles an hour. And I don't even know where you start. My question is, how often can you and the walker be in the same place? If you pass this walker, and the walker's going at 3, and you are always going at 4 or more, how can you possibly be passed by the walker? How can you even be in the same spot as the walker again? You can't. Right? Once you pass him or her, you are finished. That's it. You're going to be ahead of them all the time. Or they are finished, as it were, if it were a race. Do we know when you're going to pass them? No. We just know that you will. So I want to just tell you that although it looks like a math thing, it's just an obvious thing. If you're always going faster than 4 miles an hour and you pass someone who's always going at 3, guess what? You're not going to get passed again. At least not if it's a straight path that keeps on going. Obviously, if the path winds around and you jog in a circle or something like that, you can be passed. But okay, so how do we prove this? Again, suppose that there are 2 intersection points. And let's call them A and B. So A is like the first time you and the jogger are in the same place, and B is the next time that you and the walker are at the same place, if there were such a time. So what this means is that f of A is equal to 3A minus 2. And f of b is also equal to 3b minus 2. How do I know that? Well, if I drew the graph of the situation, 3x minus 2 looks like this. And I'm saying that however your motion is, you intersected it twice, one at A and one at B. And of course, f of A is equal to 3A minus 2, and f of b, because these intersect, is at 3b minus 2. Okay, so by the mean value theorem, and again, we should really, well, I'm going to call it MVT for now. Sometimes you see this abbreviation. By the mean value theorem, and again, we know everything is differentiable everywhere, so it's continuous everywhere, no problems with that. We know that f prime of c equals f of b minus f of a over b minus a for some c. So we know there is a c such that f prime of c is f of b minus f of a over b minus a. Now we can use these equations. We know what f of b is. We know what f of a is. So we'll plug this in. 3b minus 2 minus 3a minus 2 all over b minus a. And if you simplify this, the 2's cancel out. You get 3b minus 3a over b minus a. And this just works out to be 3. Now why is that a problem? Every f is supposed to be, every f prime, as in the derivative everywhere, is supposed to be at least 4. So how could it be 3? So actually, this cannot happen. So there are no such times a and b. There cannot be at least 2 times. So the interesting thing about this is that if you tried to convince someone who was skeptical about this walker situation, right? This walker's going at 3. I claim you cannot pass them twice, or they cannot pass you if you're going at 4. And I claim this to you, and if you're skeptical and you say, but why? But why? Okay, why can you not pass this person? And you say, well, it's obvious, right? I mean, I'm always going at 4. I've always got to be ahead of them. But how come? Well, this theorem says, you know what? Okay, suppose I'm wrong. Suppose now I'm at the same place as the walker. And then a little later, I'm also at the same place. Well, my average speed over that time was the same as the walker's speed, which was 3. So somewhere in the middle, I must have gone at 3. I don't know where. I must have gone at 3. But we said I was always going at least 4. That's exactly how the argument works. Are there any questions about that? I should write out a sentence saying, this is impossible, therefore there are not 2 intersection points, there must be at most 1. So I will leave that to you. Great. We're doing well. We're doing well. Scheduling-wise, we are doing well. So, let me move on to other consequences of the mean value theorem. And then I'll tell you about inflection points. And then we will call it quits. So here are some important consequences of the mean value theorem. I'm going to show you 3 other things that follow from the mean value theorem. So first, okay, here are 3 consequences. I'm not even going to set it up with a heading. I just want to make sure I say these 3 things in the first order, in the correct order. Okay, here goes. If f prime of x always equals 0 on an interval a comma b, then f is constant on that interval. Okay, if the slope is always 0, the function is constant. Obvious? Sure. Prove it. Prove it. Well, here goes. F prime of c, and let's assume what the hey, and f is continuous on AB, although you actually don't need this. It doesn't hurt to also fill in the endpoints. Doesn't matter. You can get around this, but I don't want to get too bogged down about it. Let's assume that f prime is 0. So we know f of c is f of b minus f of a over b minus a. Okay, so basically if we know this is true for some c. Actually, I have to be a little more careful here. Sorry. You know what? I'm going to start again. I'm going to change this to capital letters. There we go. Sorry about this. I just want to make sure I say it right. Okay. If f prime of x equals 0 on capital A to capital B, then f is constant. Okay, so here's how I do. I pick any 2 numbers. Pick any 2. A and B in A comma B. Then I can use the mean value theorem since everything's differentiable. I just want to make sure that A is not equal to B. Obviously, I don't pick the same thing twice, or else this fraction doesn't even make sense. So f prime of c equals f of b minus f of a for some c. That's just the mean value theorem. But of course, the derivative is always 0. So 0 is f of b minus f of a, and we actually proved that f of a equals f of b. Okay, so if the derivative is 0 everywhere in this open interval AB, then any 2 pairs have the same function value. All right, so that means if you pick A and B, they're at the same height. Of course, if you pick A and say B1, that's also at the same height. Any 2. In fact, if you just fix A every time and just keep picking other different points, they're all at the same height. So guess what? Every point is at the same height between A and B. And the f is therefore constant. So that's the proof. Okay? 2. Suppose that f prime of x, and this is actually the most useful thing, if f prime of x equals g prime of x for all x in some interval AB. So two functions have exactly the same derivative everywhere. They're both differentiable everywhere on this open interval AB, and they have the same derivative. What can you conclude? I ask you, people in the room, not people online. I ask you, if two functions have the same derivative, then they must be what? They must be parallel. They don't have to be the same function. How do you get two functions to be parallel? You just add a constant. There is a constant such that f of x is g of x plus c. Okay, so the curves are parallel. They're not necessarily the same, but they are shifted, vertically shifted from each other. Now, the reason this is so important is because we're going to do integration fairly soon, a couple of weeks, few weeks, we will do integration. And when we do integration, that's all about reversing the process of differentiation. And we're going to say, okay, what function has derivative equal to 2x? And the answer will be x squared, right? But maybe x squared plus 1, or x squared minus 7. Actually, x squared plus any constant has derivative 2x. Is that the only one? Yes. This says that the only thing that could have derivative 2x is x squared plus a constant. So that's why this is so important. I might as well prove it. Actually, you don't even need the mean value theorem. You just need 1, which we used the mean value theorem to prove. So why not to sketch out a proof? What the hey? If h of x is f of x minus g of x, then the derivative of h is the derivative of f minus the derivative of g, but we think these, or we've assumed they have the same derivative. Therefore, the derivative of h is 0 for all x in AB. All right, so if the derivative of h is always 0, what can we say about h? It must be constant. Yes, horizontal, constant. H of x is a constant, which I'm going to call c. It's just a flat horizontal line at some height c. And of course, this means that f of x minus g of x is c. So f of x is g of x plus c. And that is the proof. Okay? Again, you probably don't need to know that. I've never seen a question asked exactly like this, but anyway, it didn't take very long, and it's kind of important. Any questions about either of those two? Okay, let me just state the third consequence of it so you know. Again, I'm just trying to convince you why the mean value theorem is so useful by showing these nice, if somewhat obvious, facts. Here's the last one, and this is actually quite a useful fact, and we've alluded to it before. If f of x is always positive, then f is increasing. If f has a derivative that's always positive, then f is always getting bigger. Okay, that is actually a really useful fact. We're going to use this in graphing. We've said it before. Why is it true? Why is it true? Well, suppose we pick any points a less than b. Well, if a is less than b, we can use the mean value theorem and say that f prime of c is f of b minus f of a over b minus a. Now, what can you tell me about f prime of c? We don't know very much about it, but we know one thing about it. It's greater than 0. This is greater than 0. So this quantity must be greater than 0. And I don't even know where c is. There's just some c in the middle, such that f prime of c equals f of b minus f of a over b minus a. That's all we need, because we now know this quantity is positive. And since b minus a is positive, after all, A is less than B, f of B minus f of A is positive. Or another way of saying this is that f of B is greater than f of A. So think about that for a second. I just got to draw a little picture to illustrate that. Bless you. Okay, we've shown that if B is greater than A, then f of B is greater than f of A. So what does that mean? Well, we need a picture, and you'll get it in a few seconds. All right. Picture looks like this. B is anywhere to the right of A, and this means that f of B is somewhere above f of A. So this point is higher than this point, and it therefore is increasing, because it's not just true for this point, but it's true for any 2 points. It cannot go back down somewhere, because points to the right on the x-axis lead to higher points on the y-axis. That's what we have proved. Okay, so for all intents and purposes, if the derivative is positive, the function is increasing. If the same argument shows that if the derivative is negative always, the function is decreasing. And this ties into what we were doing earlier, where if the function is neither increasing nor decreasing, meaning that you're at a local maximum or a local minimum, then the derivative must be 0. It can't be positive, or else it would be increasing. Couldn't be a local maximum or a local minimum. And it can't be negative. So actually, that's the proof of the extreme value theorem that we did earlier. It's all wrapped up in what I just said there. So that comes from the mean value theorem as well. All right. All right, all right, all right. Now I have to tell you about the second derivative. Okay, we've mentioned the second derivative, but we haven't used it for anything. So now we have to see what we're going to use it for. Okay, I'd like you to consider a function that has a second derivative everywhere. There's no sort of sharp corners or something. Even the derivative doesn't have sharp corners. And what I want to do is just suppose that f double prime of x is greater than 0 for some x. So what I want to know is, what can that function look like? What does this even mean? What does it mean to say f double prime of x is greater than 0? Yes, think of this as, this is the derivative of the derivative. So think of f prime as a unit. So something's derivative is positive. That something happens to be f prime. So f prime's derivative is positive. And what did we just decide it means if the derivative of something is positive? It's increasing. So f prime is increasing. Okay, if the second derivative is positive, the derivative is increasing. That does not mean the derivative is positive. It means it's getting bigger. So I'd like to show you what that means. There's a picture, and I would like you to look at this and agree with me, or I'll talk you through it. I hope I can make you agree that the derivative, f prime, is increasing. You see, it starts off quite negative here. F prime is negative. But it becomes less negative here, and less negative, and in fact it's 0. And then it becomes positive, and more positive, and more positive. So the derivative, as in the slopes of the tangents as you move along, is always getting bigger. So the second derivative being positive indicates that the curve is what we call concave up. Think of it, a student told me she likes to remember it as up like a cup. Concave up, looks like a cup or a bowl. It could just be like this, that's part of a cup. Or it could be like this, or it could be the full sort of cup. But think of it as enclosing. If you put liquid in it, it wouldn't just run off the surface. It would sort of accumulate a little bit in it. Okay, I want you to understand that you can have f double prime of x being greater than 0, and f prime of x could be less than 0. That's possible. Here's what that looks like. The derivative is always less than 0. The function is decreasing. And yet the derivative is getting bigger. It's negative, less negative, less negative, less negative. It is getting bigger. The curve is concave up. So it is possible, yes. In fact, you could also even have f of x be less than 0 if you just shift this axis up to here. Then the function values are negative. So actually, you could have all the possibilities. The second derivative could be positive, the first derivative could be negative, and the function could be positive. Or flip these things around. It's actually not a bad exercise to try to flip them around to all 8 directions. Right? There's greater than, greater than, greater than, greater than. You get the idea. There are 8 possibilities, 2 cubed possibilities, and it's not a bad idea to draw a little swathe of a function to illustrate, yes, that you can have that combination. Now, I should tell you what happens if, on the other hand, f double prime, so let me just mark this as concave up. What about f double prime negative? What does that mean? Well, that means that the derivative is decreasing. Right? Because the derivative is the derivative of the derivative is negative. So the derivative itself is decreasing. It's exactly the same as what we said over there. And that looks like this. That looks like this. You see, the derivative is quite high here. It's quite steep, but it gets less steep, less steep, less steep until it's flat, and then it gets less and less steep. Sure, it's more and more down steep, but that actually down steepness is more negative in the derivative. So the derivative is big, big, less, 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 less. Okay, so the derivative is decreasing, and we call this concave down. And in my student's phrase, it's down like a frown. Right? It's a sad face. So concave up like a cup, down like a frown, whatever. Basically, however you remember it, you need to know the difference between them, and you do need to appreciate that you can have a negative second derivative and a positive first derivative, just like over here. F prime is bigger than 0 here, and it's less than 0 here. It equals 0 here, and yet f double prime is always less than 0 everywhere on that picture. Okay, so the second derivative does tell you something quite important. By the way, for those of you who have come in recently, I'm running a little bit late due to technical difficulties, so we'll be going for about another 10 minutes before we do homework problems. Okay. Now, I've given you the concepts of concave up, concave down. What happens in the middle? Suppose you have a curve like this. Here it's concave down. Looks like a frown. Here, concave up. There's some point where it stops being concave down and starts being concave up. And of course, if the second derivative is negative here, and it's positive here, guess what it is here? Yes, it's 0. So if f has a point of inflection, that's what this is called, at x, then f double prime of x equals 0 or does not exist. It's the same thing with critical points. Except now it's the second derivative. Okay, so what it actually is a point of inflection? Well, that's a point where it's concave up on one side and concave down on the other side. So it switches from concave up to concave down. And it's characterized by the fact that the tangent for a concave down curve is above the curve, whereas for a concave up, it's below the curve. So this tangent line here actually passes through the curve. Okay? So what I'm trying to tell you is if the second derivative exists and you have a point of inflection, that can only be when the second derivative is 0. Now, I have to tell you something quite important. If the second derivative is 0, you may not have an inflection point. Or you might not. Is a better word. Okay, so all you are doing, if you know that f double prime of x equals 0, you have a potential candidate for an inflection point, but it is not necessarily an inflection point. Here's a really straightforward example. F of x equals x to the 4th. Classic example. If you differentiate this, you get f double prime is 4x cubed, and, f prime is 4x cubed, f double prime is 12x squared. Okay, now 12x squared is 0 when x equals 0. F double prime of 0 is 12, 0 squared is 0. Okay, if we get this wrong, we are going to say, oh yes, the second derivative is negative, therefore we have a point of inflection. But that is not true. Look at the curve. It's a minimum. It's a local minimum. It's not a point of inflection at all. Y equals x to the 4th. Not a point of inflection. So it's a trap. It's a trap that you should not fall into. Second derivative 0, you might have a point of inflection. You might not. But if you do have a point of inflection, you know the second derivative is 0. That's how it works. So if you do want to find points of inflection, yes, by all means, find the zeros of f double prime, but do not assume that they are points of inflection. They are just candidates for points of inflection. All right, so we're going to be looking at more of that next time when we do graphs. So I'm just going to do one more thing today, which is to set up another thing that we'll need when we're doing graphs. And that is, I would like to show you how to classify critical points. And I'll give you just one example using two different methods. So this is in section 11.5. It's the last part of chapter 11. Okay, suppose that you have a critical point. So f is smooth, and in fact, when I say critical point now, I'm going to forget about the case where it doesn't exist. I'm going to assume that f is perfectly smooth, has a derivative, second derivative, no problem. F prime of c is 0. What could possibly happen? What are the possibilities? Well, there are 4 possibilities. Really 3, but 4 possibilities. And I'm just going to draw little pictures of them. You might have a local maximum. You might have a local minimum. Or you might have a point of inflection, horizontal point of inflection.